No. No, ma'am.
ओके, तो आपसे क्वेश्चंस हो रहे हैं. Is there any difficulty in solving the question? Yes.
No.
Okay, so the next method of preparation is halogenation of alkenes. Okay, so we have discussed the halogenation of alkane, right? Now the topic is next method of preparation is by halogenation of alkenes. Okay, let's see. Yeah, suppose if I take ethene. Yeah, so this is ethene. So on treating the alkenes with halogen atom, right? Suppose X2, dihalogen, right? So it will form your vicinal dihalide. See, so what happens here when any alkenes they are treated with halogen, right? So they form vicinal dihalide. Means what is vicinal dihalide? So basically the substituents on adjacent carbon. You can see the XX, right? The halogen get attached to the adjacent carbon, right? Means a neighbor's carbon. So basically, what is vicinal? So vicinal comes when the substituent are on the adjacent carbon atoms, right? And here's another word, geminal. You should know what is geminal and what is vicinal. So ये दो words हैं. These words we use when the substituents for vicinal, when the substituents are on adjacent carbon atoms means the neighbors, right? Means the functional group or the substituents are the neighbors, right? They are attached to the adjacent carbon atoms, so they are known as vicinal, right? They are known as vicinal type of halides. So basically they are halides, right? So we can say that they are vicinal dihalides, right? So just remember what is vicinal. So when the substituents are present or attached on the adjacent carbon atom, right? Agal-bagal, neighbors. So they are known as vicinal. And what are geminal? So geminal are those groups. They are used, this word is used basically when the substituent are present on the same carbon atom. When the substituent are present at the same carbon atom, then we called it as a geminal. For example, this carbon, same carbon atom pe if two halides are present. Okay, so we called it as gem dihalide. Okay, we called it as a geminal dihalide or gem dihalide. Got it?
Yes.
So yeah, so basically the halogen of alkenes, it gives you vicinal dihalide. Okay, so what you have to do when any alkenes is given, right? So just break this bond, this double bond will be break down, right? And attach these, this is X2, right? Means two halide is there, right? Two halogen group is there, right? So you have to just attach the halide group on the adjacent carbon atom, right? So basically you will get vicinal dihalide in this case. For example, if I give you one question, okay, so if I take again, I'm taking the ethene. Right, so this is ethene. When I give you Br2, right? So tell me what is the product? What will be the product?
Ma'am, CH3.
Yeah. No, it's CH2. This is CH2,
CH2,
right?
sorry.
Yeah, it's
Yeah,
CH2. And this bond will break down, right?
break.
So
Yes, ma'am.
This is again CH2, and here bromine group will attach, and at the same adjacent group, adjacent carbon, again second bromine group will be attached. Okay, so basically this will give you vicinal dibromide. This is your vicinal dibromide. Got it?
Yes, ma'am.
Marwa, clear?
Yes, ma'am.
Yeah, just note down one thing. So basically, this bromination, right? Bromination is used as a test for unsaturation, right? Whether your compound is unsaturated or not. Okay, so see, you can write down. Uh, as a note, you can write down. So basically, bromination is used as a test for unsaturation, right? So basically, any unsaturated, um, for example, any unsaturated your compound like your alkene. Okay, so if it is ethene, so when you do the bromination of ethene, so basically this bromine is which color? So it's a brownish red color, right? Bromine water किस color का होता है? तो basically it's a brownish red color, right? So when you treat any unsaturated compound with bromine, right? So basically you will get, again you will get the vicinal compound, and this vicinal dibromide is basically a colorless, right? It's a color. You will get the colorless compound. Okay, when you add bromine into any unsaturated compound, then you will get a colorless compound. So basically, alkene decolorizes bromine water, right? So alkene decolorizes bromine water. So that's why the bromination is used as a test for unsaturation. Okay, yeah, you can
Yes,
write down
ma'am.
alkenes decolorizes, because we know that the bromine is brownish in color, right? So when you add alkene or any unsaturated compound into bromine, right? Or when you add bromine into any unsaturated compound, you will get a colorless compound. So basically, alkene decolorizes bromine water. Okay, so that's why bromination is used as a test for unsaturation. So you get to know if the compound is unsaturated or not. अगर वो unsaturated compound नहीं होगा, saturated compound होगा, then it will not give the test. Okay, you will not get the colorless compound if you add the saturated compound over here, right? So only alkene decolorizes bromine water. Alkene or alkyne, right? Any unsaturated compound. So alkene decolorizes your bromine. Okay, let's do some question. Okay, you have to write down the product name. Okay, do this. What we have to do? So we have to write down the product name. Okay. So it's very simple. It's the halogenation of alkene. Okay, I just told you it will give you when you do the halogenation. So when you treat it with bromine, so this bond will break down, right? And just attach one bromine here at this carbon and one bromine here, right? So you will get one bromine here, and one bromine here. Right, so this will be your final product. Okay, sometimes the students, what आप लोगों को मैंने देखा है, what you guys do, so basically आप यहाँ पे क्लोरीन ब्रोमीन लगा देते हो, so that's wrong. Okay, you are removing one carbon from here, right? तो यहाँ पे क्या है, again a one carbon here, right? So carbon को extend करना है आपने, यहाँ पे carbon लगा हुआ है, and you have to add the halogen atom, attach the halogen atom to this carbon, right? So you have to add like this. Okay. See, if you uh, if you write down this product, right, so this will be wrong. Why? You can see over here, this is one carbon, second carbon, and what about the third one? Right, you can see over here the in the reactant part, one carbon, two carbon, and third carbon, right? So आप यहाँ पे remove कर दे रहे हो one carbon को, so that's wrong. Now see, this is the correct answer. So you one carbon here, second carbon, and the third carbon, and after that you have to attach the bromine. So that's the product. To the second, third, and fourth. See the double bond, just remove the double bond and attach the halogen atom to this. Right. Double bond ke terminal pe you have to attach the halogen atom. Both the halogen atom.
Ma'am, it will the bond will break
Yeah.
and will add the chlorine there.
Yeah. Here one chlorine is one chlorine
And
here,
yeah,
right?
yes, ma'am.
So this will be your final answer. Yeah, Marwa, third one. Tell me the answer of third one.
Yes, ma'am. First, the double bond will be broken and then the Br will get added to there.
Yeah. So you will get this one bromine here and one bromine here. This is a final product. Okay, similarly for the fourth one, just break the double bond and one bromine will attach here and one bromine will attach. Okay, so that's the final answer. Then, have you guys written till here?
Oh, ma'am, writing.
Okay, just write down till here, then we will start the physical properties. Okay, so we have completed the methods of preparation of haloalkane, then your physical properties.
Ma'am, done.
Let's see properties. physical properties of haloalkenes. Right. So first, let's talk about the color of alkyl halides. So color. So basically, alkyl halides, basically they are colorless in nature when they are pure, right? But bromide and iodides, right, they develop color when they are exposed to sunlight. Okay, when they are exposed to light, they decompose into halogens, right? Further halogens, and they develop basically a color. Okay, but commonly, generally, alkyl halides are colorless in nature when they are pure. Okay, so write down. So when alkyl halides are colorless when pure, but bromides and iodides develop color when they are exposed to light. Because when they are exposed to light, they just decompose into corresponding halogens. Okay, for example, if it is 2 moles of Ri, okay, alkyl iodide. So when they are exposed to light, right, when they are exposed to light, so they just decompose into R plus your I, right, your corresponding halogens. So that's why they impose color. Second, your melting point. First, let's talk about the boiling point. Okay, so see, so basically halogens are polar in nature, right? Haloalkenes, not halogens, haloalkenes are polar in nature, and basically their boiling point is greater, right? Because we know that they are made from the hydrocarbon part, right? Parent hydrocarbon part. When the halogen is attached to the hydrocarbon part, it will give you haloalkanes. But your haloalkanes are more polar, right? And their boiling point is greater than their parent hydrocarbon, right? So the boiling point is higher, and you can write the boiling point. Suppose if it is parent hydrocarbon is RH, okay, and your corresponding your haloalkane, which is made from this parent hydrocarbon, is your RX, right? RX. So always remember the boiling point of this haloalkane is greater than its parent group, right? So its RX is always greater. The boiling point of RX, haloalkane, is always greater than their parent hydrocarbon chain. Okay, and also due to the molecular weight, right? Because boiling point is is directly proportional to the molecular weight. If the molecular weight is more, then the boiling point is more, right? So if you compare the Rx, right, if it is your fluorine RF, or RCl or anything, no, then you will observe that the molecular weight of this haloalkane is more than that of hydrocarbon, okay, is more than that of hydrocarbon. So that's why the boiling point of haloalkane is greater than its parent hydrocarbon. Got it?
Yes, ma'am.
Yeah, so write down, since haloalkenes are polar, their boiling point is an parent hydrocarbon, and the boiling point is higher also due to larger molecular mass. Molecular mass. Right, the haloalkane has higher molecular mass than that of your parent hydrocarbon. That's why the boiling point is more. And yeah, one more point. And basically, the boiling point is directly proportional to the number of carbon atoms. Okay, if the number of carbon atoms is more, then the boiling point is also more. For example, if I give you your CH3X, another one is your CH3CH2X, another your CH3, CH2, CH2X, and CH3 and CH2, means I'm just increasing the chain, right? मैं increase कर रही हूँ chain and the number of carbon atom. So what I said that for a given halogen atom, the boiling point is directly proportional to the number of carbon atoms. Okay, so tell me which one has the greatest or larger boiling point. If it is first A, B, C, and D. Right. So which compound has the larger boiling point? You have to check the number of carbon atoms. If the number of carbon atom is more, right, then that compound has larger boiling point, highest boiling point. Okay. Yes. Marwa and Ayesha, tell me A, B, C, or D. Which one has the highest boiling point?
Ma'am, option D.
Yeah, it's D, right? Because you can see over here, 3 carbon and 1 carbon. That is 4 carbon atom is there, right? So the number of carbon is more, so it has more molecular weight is more, right? Its molecular mass is more. And if it is molecular mass is more, then it has a highest boiling point, right? So for a given, and yeah, if the same halogen group is there, अगर यहाँ पे different halogen group होगा, then you will not use this point, right? If it is, this is for the same halogen group, for a given halogen atom, right? Given halogen atom, then boiling point is directly proportional to the number of carbon atoms, right? If the halogen atom is same in all the 4 options, right? If I write Cl here, right? In all the 4 options, the halogen group is chlorine, right? If the halogen atom is same, then you have to use this. The boiling point is directly proportional to the number of carbon atom, right? And if so, in this option, what is the order? So D has the maximum boiling point. After D, this 3 carbon atom is there, right? So after the C, then P, then right. So this is the order of boiling point. Order of boiling point. Maximum you will see in the D option and the minimum you will see in the A option. Okay, methyl halide. Clear?
Yes, ma'am.
Alma, why are you not responding? Is it clear?
Yes, ma'am.
Okay, if any doubt, you can ask in between.
Okay.
Next point. Boiling point is directly proportional to the molar mass of your halogen atom. Molar mass of halogen atom, right? So the halogen atom which has the highest or larger molar mass will have the highest boiling point. Means if it is fluorine, chlorine, bromine and iodine, right? So iodine क्या है सबसे ज़्यादा highest, इसका molecular molar mass is highest, right? It has a larger molar mass. And fluorine, above these four, fluorine has the minimum, right? So what will be the order? So order will be your RF, it will have the minimum boiling point, then RCl, then your RBr, then you will see the boiling point, the highest boiling point in your iodide, alkyl iodide, right? So alkyl iodide has a maximum boiling point and your alkyl fluoride has the minimum boiling point. Okay, so boiling point is directly proportional to the molar mass of your halogen atom. And we know that molar mass of iodine is highest above these, right? Iodine का सबसे ज़्यादा होता है, after iodine, bromine, then chlorine, then fluorine. Fluorine has the minimum molar mass in these four, right? So that's the order of boiling point. Order of boiling point. For a given alkyl group. For a given alkyl group, the boiling point is directly proportional to molar mass of your halogen. And yeah, one more point is there. Just keep in mind, boiling point is inversely proportional to branching. More the branching, less will be the boiling point. Okay, more the branching, the less will be boiling point. Remember that. Suppose, if I take this, bromobutane, 1, 2, 3, 4, 4 carbon. Okay, means your this. Second, I just take this. Third compound is this one, right? If it is A, B, and C, right? So which one has the maximum boiling point and which one has the lowest boiling point? Just tell me the order of the boiling. Order according to the boiling. Because we know that, see, the boiling point is direct inversely proportional to branching, right? So branching, जितनी ज़्यादा branching होगी उतना कम boiling point होगा, right? So you can see over here there is no branching, right? So this is a straight chain. This is the straight chain. So इसकी maximum होगी. Then you can see over here there is a one branching. But here there are many branching, right? So basically this is your mini branching यहाँ पे, तो इसमें सबसे minimum होगा, right? So we know that boiling point is inversely proportional to branching. More the branching, less will be the boiling point and vice versa, right? So you can see here the more branching is there, right? So it will have the lowest boiling point. After this will have the boiling point and the highest boiling point you will see here, right? Because there is a no branch. No branching you can see over here. This is a straight chain, right? So bromobutane. So it has the maximum boiling point. Got it?
Yes, ma'am.
Okay. Let's give one more question. Let's see one more question. Write down the question. Arrange each set of compounds in order of increasing boiling point. Boiling point. First one, bromomethane, then bromoform, then your chloromethane, after that dibromomethane, right? So these are the four compounds. You have to arrange this in order of increasing boiling point. Second one, 1-chloro-propane, isopropyl chloride, and the third one is 1-chlorobutane. Yeah, do this. You have to arrange each set of compound in order of increasing boiling point.
Is it chloromethane, bromomethane, then dibromomethane, and then borophor?
Again, just tell me.
Chloromethane,
I'm just my name there. You A, B, C, and D. Okay, just tell me accordingly.
C, A, D, B.
C, A, D, and B. Okay. According to you, C has the highest boiling point, highest or lowest?
Highest.
Oh, yes, Ayesha, tell me your answer.
Ma'am, bromomethane first. It has more boiling point. Then chloromethane.
C, yes,
Then dibromomethane
then your B.
and bromoform.
Okay, let's see. So it's CH3, first for the structure, Br, yeah. And the second is your bromoform. So it's CH3. Third structure, it's CH3Cl, right? C and your CH2Br2, right? So that's the D part. Okay, now see, in First, you can see over here there are two halogen groups. In three compounds there are bromine group, and in the one there is a chlorine group. Now just tell me accordingly. So molar mass of which is larger, chlorine or bromine? You can see the order of boiling point. It's in Br में सबसे ज़्यादा होता है, then Cl, right? So in all these, chlorine will have the lowest boiling point. Okay, because the halogen group, it has the lowest molar mass, right? Between these two, when you compare bromine and chlorine, so which one has the lower molar mass? Obviously chlorine, right? Chlorine has a lower, yeah. So you will see that this CH3Cl will have the lowest, right? इसकी सबसे lowest होगी boiling point. Okay. Now let's compare these three, A, B, and C. Okay. Now we have see that it is for a given halogen atom, boiling point is directly proportional to the number of carbon atom, right? Number of carbon atom. Or you can see that the number of carbon atom is same. You have to check the halogen group. You can see over here there is only one halogen group, right? So the obviously the molar mass is less as when you compare CH3Br, CH2Br2, and CHBr3, right? So the more the number of halogen group, more will be the molar mass. More the number of halogen group, you can see the more will be the molar mass. When you compare the molar mass between these three, you will get it has the maximum molar mass, right? CHBr3 means your bromo form has the maximum molar mass. Okay, and molar mass, you can see that molar mass is directly proportional to the boiling point, right? So this CH bromo form, it has the maximum boiling point. B, right? B has the maximum boiling point. Now between these two, between A and this is your D part, right? You can see Br2 is there and there is only one halogen group, right? Here in the D part, there are two halogen groups, right? Br2, bromine is 2 and here only one bromine is there, right? So between these two, which one has the highest molar mass? Between these two, which one has the more molar mass? Tell me. We have to see the number of halogen atom, right? So in this, the Br2, the halogen atom is 2, and in this, bromine is only 1. Halogen is 1, right? So obviously, they will have the highest molar mass. Between these two, D की क्या होगी? ज़्यादा molar mass है, right? CH2Br2 has more molar mass than this, right? So after B, the order will be E, and after D, it's A. And the lowest molar mass, the lowest boiling point you will see in your CH3Cl. CH3Cl means your C. Yeah. Got it or not? Got my point or not? How to compare the compounds?
Yes, ma'am.
Aisha, any
Yes, ma'am.
doubt? You have to keep all the point in your mind, right? सारे points को आपको देख के चलना है. You have to compare all these, right? So this will be the order of boiling point, right? Now do the second one. Accordingly, just first draw the structure and accordingly do the first one is chloropropane. One chloropropane. 1, 2, 3, and on the first position is chlorine. Second is your isopropyl chloride. Isopropyl chloride. So it's a propyl and it's an iso structure. So you will see the branching over here, right? So chlorine will be attached here. Third one is 1 chlorobutane. 2, 3, 1, 2, 3, 4, and chlorine group, right? Okay, now arrange this. Mm, You have to see the branching here. And we know that branching, the boiling point is inversely proportional to branching, right? So in the second one, in the isopropyl chloride, you can see the branching over here, right? So it has a minimum boiling point. If I give A, B, and C. Now I have given you the hint. Now just tell me the order.
Ma'am, first isopropyl chloride because it has branched structure.
Okay. It will have the minimum. It will have the minimum boiling point.
Yes.
Yeah. And after that,
Then chloropropane
okay,
because
fluoropropane.
um then chlorobutane.
Very good. Okay. The more the number of carbon atom, the more will be your boiling point. Okay, because we know that boiling point is directly proportional to the number of carbon atom, right? And boiling point is inversely proportional to the branching, right? So in the second, in the B part, B option, the branching is there, right? So it will have the lowest boiling point. And after that, when you compare A and C, right? So you can see the number of carbon atom in first is only 3, right? But in the C part, there are 4 carbon atom because it's butane, right? So the more the number of carbon atom, more the boiling point. So maximum boiling point you will see in the option C. Okay, bromo, chloro, butane. Okay, right on. Yeah, that's a case of melting and boiling point of. Boiling point of the haloalkane will be the same, right? Boiling point and melting point, right? So that's where that will be the order of boiling point and melting point as well. And yeah, when we talk about the haloarenes here, so see. So basically, the melting point of your, for example, if I draw 3 structures, if I draw your para dichlorobenzene, right? So this is your para position. So one, two, three, and this is your fourth, fourth carbon, right? So what is this? This is your para dichlorobenzene. This is your para dichlorobenzene, right? If I draw the meta and ortho one, let's draw it. So meta will be, if it is chloro, so according to this, this will be your meta position, right? So this is your meta. So 1, 2, 3. Meta dichlorobenzene. If I draw the ortho dichlorobenzene, right? So if it is chlorine, so accordingly, it's the ortho position, right? So it's ortho dichlorobenzene. Okay. Now see, when we talk about the melting point of these three, okay, so basically the melting point of para dihalobenzene, any halogen group, if it is chlorine, fluorine, bromine, iodine, anything, right? So the melting point of para dihalobenzene is always higher than that of ortho and meta. Okay, why? Why? Because you can see the symmetrical structure is there, right? Because para isomers are more symmetrical in nature, right? And their molecules, they are they are, you can say, packed closely in the crystal lattice, right? But due to the symmetrical nature, when you pack this structure, your para structure in the lattice, so it will be very easy for you to pack closely in a crystal lattice. So which leads to a stronger molecular force of attraction, right? So in this case, in para-dichlorobenzene case, as you can see, it's a symmetrical. You can see 1, 2, 3, 4, 5, 6, right? So it's a symmetrical. You can see the symmetry over here, right? But in these two, you can't see the symmetry, right? These two are unsymmetrical. Symmetrical. Para one is your symmetrical, and these two are unsymmetrical. Unsymmetric. Okay, so you can write down here the melting point of para dihalobenzene is always higher than those of the ortho and meta, right? Meta isomers. Okay, so melting point of para dihalobenzene is always higher than those of the ortho and meta. Okay, if I give you three compounds, okay, if one is your para, right, if second is your meta, and then is your ortho, right, ortho group, then always, if I ask you which one has the highest melting point, so just remember para dihalobenzene has the highest melting point above these. Okay, okay, right on the reason also, due because para isomers are more symmetrical and hence their molecules pack closely in the crystal lattice, which leads to stronger molecular force of attraction. Force of attraction. Right, so it has a maximum melting point. Got it?
Yes, ma'am.
Okay, now write down. Now write down. This one. Written?
Yes, ma'am.
Okay, let's talk about the solubility of haloalkane. Okay, next physical properties is your solubility. Okay, so just remember haloalkanes, they are polar. We know that they are polar, but they are miscible with water, right? Why? Because they neither form hydrogen bond nor they break the already existing hydrogen bond. That's why they are immiscible in water, right? Just remember that. Because with the haloalkanes, we know that they are polar in nature. But instead of the polarity, polar in nature, they are immiscible in water. Because when haloalkanes is added in water, when you put the haloalkanes in water, the new bond which is formed, they neither form hydrogen bond nor they break the already existing hydrogen bond. Okay, because the new attraction of water, new attraction of water and haloalkanes is very, very big. Okay, so due to the weak intermolecular force of attraction, they don't, they are not, they are immiscible in water. They are immiscible with water. But the haloalkanes, they are soluble in organic solvent. Okay, like your the low polarity organic solvents like your ether, your benzene, right? So haloalkanes, they are soluble in organic solvents just like your ether, benzene. Okay, because in that case, when you add the haloalkane in your organic solvent, then the new intermolecular forces, they are much similar to those in the low polarity solvent. Okay, that's why they are miscible in liquid, miscible in organic liquid, but they are not miscible in water. Got it? Let's write down. So basically, haloalkanes are immiscible with water. Why? Because they neither form hydrogen bond nor break the already existing hydrogen. Why? Because the new attraction of water, force of attraction of water, and the haloalkanes is very much weak, is weaker. But haloalkanes, they are soluble in organic solvent, which has low polarity. like your benzene, ether, etc. Okay, so just remember when RX, right, when you haloalkanes, they are dissolved in water, new interactions came into play. Okay, between the water and your halogen group. Between your water and halogen group, and this new force of attraction is basically much weaker than hydrogen bonding between the water molecules. Okay, that's why the your haloalkane is immiscible in water. Okay, sometimes a question may come like why haloalkanes are immiscible with water? Because haloalkanes they are polar in nature, but why they are immiscible with water? Okay, so just write down this. Because haloalkane, when you dissolve the haloalkane in water, new force of attraction comes into play, right? Between your water and your haloalkane, your RX, right? Between your RX and your water, right? So the new force of attraction between water and your RX is much weaker than your hydrogen bonding between water molecules. Okay, so hence you can write hence your RX is immiscible in water, right? But they are miscible in organic solvent, low polarity organic solvent. Here, any doubt till here?
No,
No, ma'am.
Okay, write down. Written?
Yes, ma'am.
Okay, okay. I think the time is up. So, inshallah, we will continue in the next class and we will start the chemical properties of halogen, which is very important. We will discuss the nucleophilic reactions. Okay, we will see electrophilic substitution reaction and many more. Okay, so please be there on time. Okay, so that's all for today. See you in the next class.
Thank you, ma'am. Allah Hafiz.
Okay, Allah Hafiz. Take care. Okay, hello Aisha.
Assalamualaikum, mom.
Walaikum Assalam. How are you?
Alhamdulillah, I'm fine. How are you?
I'm good. So have you revised the previous topic? Everything is
Yeah,
clear,
mom.
right?
Mom,
Any
in
doubt?
the homework that you gave me, the first question,